The resistance of the thermistor. And again, in this case, we use Kirchhoff's second law again. And how do we do that one? We use Kirchhoff's second law because we want to know the resistance of this thermistor. And it is part of this loop. Of course, I could use another logic, but I prefer Kirchhoff's second law. The more we use it, the more easier the questions become. So what am I going to do? I'm going to say, okay, in this loop, there is this EMF, there's the potential difference across this, and there's the potential difference across this. Since I now know the current going through this is the same as this, is the same as this, then I'll come here and I'll say the EMF here is equals to the potential difference across the 3400 ohm resistor, which is current times the resistance, and the potential difference across the thermistor, which is current times the resistance of the thermistor, RT, and the potential difference across the 5800 ohm resistor. After all, it's 3.6. Why? Because if 9.6 is applied by the battery and 6 is across the resistor, the thermistor, and the 3400 ohm resistor, then the remainder 3.6 volts will be across the 5800 ohm resistor. So knowing this, we go further now. We calculate, multiply this, we calculate it and add it to 3.6. Then we get 5,700 and 5.708. So when you take this 5.708 to the other side, you subtract it, 9.6 minus that, you get this. Then you get your RT as 6.3 times 10 to the power of 3. So the resistance of the thermistor is this one. We found it using Kirchhoff's second law. Then the next, the question asks us, the initial energy stored in the battery is 2.6 times 10 to the power of 4 joules. Assume that the EMF is constant at 9.6 volts, as we know from that circuit. Determine the final energy stored in the battery after the charge 330 coulomb has moved through it. So the charge has moved through the battery. Okay, so to do this, we need to know the final energy stored by the battery. Remember, the battery stores energy as chemical energy. So we need to know the final energy that it has left. But to know what it has left, we must know what it has supplied. Now, to know what it has supplied, we must understand the definitions of EMF. The first definition of EMF says energy converted from other forms into electrical per unit charge passing through the source. So as you can see, there's energy that has been converted to electrical energy per every unit charge passing through the source. The other definition says the work done to move per unit charge, the work done per unit charge to move a charge around the circuit. So are these definitions different? No, they're not different. The first one, which says energy converted from other forms to electrical, is the same as the one which says work done to move energy per unit charge to move charge throughout the circuit. Because what happens is that every unit charge gets electrical energy from chemical, and this electrical energy is what facilitates it to be able to be moved around the circuit. So for there to be work done to move it around the circuit, energy must be converted from other forms to electrical. So ultimately, the doing of the work to move it around the circuit and the giving of electrical energy are one and the same thing. So you're giving electrical energy so that we can move something around the circuit. So ultimately, it's the same thing. It's like giving a child money so that they can go to school. So I can easily jump the process of saying that I gave my child money to go to school by simply saying that I send my child to school. Because it is the same thing, giving them money to go to school and then them going to school and using that money. It is the same thing, you see. So them using the money to go to school cannot be separated from me giving them money to go to school. Ultimately, the amount of money that I gave them to go to school is the amount of money that they used to go to school. So the process is the same. So the definition of EMF becomes W over Q. We should not be confused why we use W. We use W because we want to use E for what is it? You want to use E for EMF. So W, we then use it for since we have already said that the definition of EMF can have work done per unit charge, then W comes from there. But we know that this W doesn't only represent work done, it also represents the energy supplied from other forms to electrical, so that work can be done to move the unit charge throughout the circuit. So EMF by definition then becomes W over Q. So W represents energy supplied as much as it represents the work done. For there to be work done, energy must be supplied. So the work done, W, is equals to the EMF times Q. So the energy supplied, W, can be found this way. So this is the energy supplied by the battery. So knowing the energy that the battery had at first minus the energy it has applied, we can find the energy left. So that is the energy we write here. So just let me just pause a bit.